Hello and warm welcome to all of you Pythonistas out there. In today's tutorial you will learn how to make animated lighthouse maps for any country in the world. First things first, let's use pip install and install the packages that we will need. The first one is definitely OSM-NX package for fetching OpenStreetMap data, then GeoPandas for working with geospatial objects, Contextually and XYZ services for fetching base layer maps, Matplotlib for creating the map, Shapely for working with vector files, and finally Pillow for publishing this as animated GIF. And let's go ahead and load these packages or import them. The first one we will import is the pathlib package, which allows us to set up the path for saving our file. Then NumPy, of course, for data wrangling. We will also need a pandas for the similar thing. And then after that, a number of other packages such as GeoPandas, which we will use for working with the geospatial objects, including the coordinates reference system. Then Shapely for working with vector files specifically, because when we use this OSM-NX package, which we also loaded, we will be working with OpenStreetMap data, which comes in as a vector format. Then Contextually we'll be using for the Basemap layer, in this case CartoDB. And then Matplotlib, we will be loading here several packages. PyPlot, of course, for creating the graph or the map itself. And then here also for the animation, for creating animation is Func animation, and then Pillow Writer for actually saving this as well. And then finally here we'll be also using this RC package for turning this animation, so publishing this animation here, which is going to actually show us the animation inline in the Jupyter Notebook, which we will be using in today's tutorial. The first step is, of course, to fetch the data that we need. So we'll be using OpenStreetMap data from Overpass. And to actually speed things up, we're going to be defining here a few things. First of all, we're going to be caching the data here. So that's why here in the settings I use this cache. The second thing, we are also going to be using the quiet logs. And then we're also going to be erasing here the allowable query area size. So this matters because it actually offers us faster reruns, fewer API hits, and also single-shot country query won't be rejected for being too large. Now, after this is done, we're going to be fetching the boundary for Greece. This is the country for which we're going to be creating the animated map. So simply this geocode to GDF, takes the data here, and then here I also included to throw an error if it could not actually find the Greece data, or if it's actually empty this call. But in our case, this is going to be fine, as you will see actually in the continuing this tutorial going forward with it. So there are two sources of lighthouses OpenStreetMap data. The first one lies within this man-made lighthouses. So over here, what we're going to do, first of all, define the tags here. So what is the key? Man-made, and then the value, which is actually lighthouses. And then what we're going to do after that, we're just simply going to build a query that will be then passed to the Overpass. And this is going to fetch the first amount of data. For that, what we're using here, as you can see, features from place. And then we're passing here again Greece, and then also providing these first number of tags. Now, the second source of lighthouses that exists in OpenStreetMap data lies within this CMark type, where we have several possible values: light major, light minor, and lighthouse. What we did in the previous step, we're just going to replicate it here. So we're here going to create these tags, where the key is the CMark type, and then the values are these three, so light major, light minor, and lighthouse. Mine's here, I'm using actually strings, so double quotes. And then over here, we're just again defining the Overpass query, but this time for these second, type of features, but exactly the same function and also exactly the same values here for the Greece. Now we're going to actually go ahead and build a compact attribute schema present in at least one of these two sources. And we're doing this because it's going to keep the memory and plots lean, and only attributes you might label or filter are kept from here on. So what we are actually doing is writing here basically for statement, and then only for those that exist here in these two possible data sets, only those columns we're going to be keeping them. And this is very important for our next step, where we actually going to union these two data sets. And of course, that means they need to have the same column names. If you previously worked with OpenStreetMap data, you know that it comes in different formats, so polygon, line, or multi-polygons. So what we're doing here, we're going to convert any geometry to points for uniform plotting. So we're going to prefer a representative point guaranteed inside the polygon and falls back to the centroid. Why this matters is because OSM data features can be different, types of points, lines, and polygons, as I mentioned before. And for the scatter plots that we will be using matplotlib, we definitely need points. And that's exactly what this function toPoint is actually going to do. Of course, the first thing is going to filter out if the geometry is empty. So in that case, it's not going to return anything. And after that, when it returns the geometry, as we said, it is going to return it as a point, even though it could be actually defined also as a polygon or a multi-polygon. This step is very important for us because essentially this allows us then to have a final number of lighthouses that we will then use in the next steps to actually map the lighthouses. Once this is complete, we have another set of data wrangling, and this time we're going to be selecting a minimal set of columns. Then we're going to be transforming these previously selected geometries to points. We're going to be dropping empty geometries and then setting the active geometries. Why this matters is that it's going to create two consistent point-only layers, which are going to be then ready to union and plot in the next steps. And this is what this normalize function does. It's a function of this GDF object. And in these columns, as you can see here, only selecting those that exist and that have this geometry column, and then applying also this previous function toPoint that we had created, dropping, of course, the missing values and then subsetting those that have the geometry column there. For the rest, simply setting the geometry value and then returning here at the end this object G. And then as a last step here, we are simply going to apply this normalize function to both of our data sets. So both A dataset, the one that comes using the tag A, and the B dataset that is a product of the tag B. So far so good. So we put into order these two datasets, we made them compatible, and now in this step what we're going to do is union and deduplicate by exact geometry. So what does that mean? It means that we are going to be concatenating, so merging these both sources into a single geodata frame. And not only that, we are also going to be carrying over the coordinates reference system, or a CRS, from whichever is present, so either A or B. We are doing this because this is going to merge the two tagging systems into a single lighthouse set, and it's going to make it possible that we use just one data set in the following steps when we are mapping things. So in the code here, what you can see is why we loaded actually pandas at the beginning, because now we can use this concat function to union the dataset A and dataset B into a single one, and then in the next step taking the coordinates reference system either from one or the other. In this case, it's going to be pretty much the same. Now, in the second step, what we're doing is we're converting each of these point geometries to WKB bytes, and then dropping the duplicates by identical position. Now, this second step is important because actually it eliminates double entries where the same lighthouse is tagged in both schemas. Essentially, we're ending up only with the unique number of lighthouses. So what we did here in summary, we actually did, we merged two days, we unioned them, and in the end, we just simply, drop the duplicates. Since base maps are working with the pseudo-Mercator coordinates reference system, which is this 3857, we are going to go ahead and just convert our grease boundaries also to this coordinates reference system. So we're going to go do that first, and then in the second step we're going to also do that for this lights dataset that we just merged together. So essentially there is no difference here, it's the same, and it's the same function to CRS. In this step, we're going to go and compute a padded extent based on grease boundaries. So what does this mean? So given the 4 coordinates of the bounding box here, we're going to actually go and calculate a slightly padded map extent, so 5% around the border of grease. And the reason why we're doing this small exercise is we are actually want to avoid tight cropping and show really nice framing for the upcoming base map and animation. So we're here defining, of course, the bounding box, the bounds, so minimum x, minimum y, maximum x and maximum y, so longitude and latitude. And then this pad ratio, 5% is this 0.05. And then over here, what we're doing is we are simply defining here the extent based on this pad ratio. So just kind of a bit readjusting the bounding box or the bounds of our map using this new pad ratio. And then in the end here, what we are doing with this length is simply we're checking did this actually take place here, and what are the new bounding box coordinates. Okay, so the first thing we're going to do here is create a static figure with the help of matplotlib. So we're defining here as a fig and then calling from matplotlib the subplots. Over here, what we're going to do, first of all, define the figure size in inches, so 8 by 8. And then we're gonna also here set the axis off, so we're not gonna show them on the map. And we're also gonna set here our longitude and latitude limits. So for the longitude limits, so this xlim, basically those are the first 2 parameters of extent. And then for the latitude or y limits, those would be the 3rd and the 4th element of this extent. Of course, because in Python index starts at 0, that's why we're here also starting with 0 and going all the way to 3. Then we're going to be adding the base layer so that we have the context, and we're going to be using a dark matter from CartoDB. You can check the website of this one. There are also other options, but this one is basically going to have a dark background. So we're here using contextually providers and then calling here the dark matter. And then right away, we are again using contextually and adding this base map to our main plot. And of course, the coordinate reference system needs to align. So we are here adding the pseudo-mercator, so this EPSG 3857 to our plots. As we're working with the base layer, we're also going to add here very subtle grease boundaries so that we actually can, outline where grease lies on this base layer. But we're not going to here choose something very thick and too strong, and that's why the line width here is not that pronounced. The transparency is also a bit higher, and we're also taking the white color but without actually accentuating it too much, because we don't want this to overpower the lights on the map. And as a final component, we are adding also lights, which are actually points. That's why we're using scatter from the matplotlib. And over here we are passing right away lights 3857, so those that are reprojected. We're using, of course, from the geometry x and y points, so longitude and latitude. So for scatter plot, you need to have x and y. Then we're choosing here the size of the lights. So 8, the base lights are going to be white. They're going to be, the transparency is going to be lower, so they're going to be more visible than the border that we previously defined, so they actually still stand out. And this is how the base map, so the static map, looks like, the non-animated, the base layer. And now you can see, of course, also the distribution of the lighthouses. In the next step, we're going to go ahead and define the parameters for the animation and, of course, animate our map. All right, in this part, we're going to go ahead and animate our map. But first of all, we're going to be defining some constants here. First of all, we're going to have a squared map. So it's going to be 600 by 600 pixels. Then frames per second is going to be 18. So this is going to be for a very smooth animation. The duration of the whole animation is going to be 8 seconds. Blink period for the lighthouse is going to be 3 seconds. And I chose here a bit lower dots per inches, so DPI, only 100. Because I wanted actually to have a bit smaller file in the end. And then we're also going to have some derived figures here. So the figure size is simply here going to be converted to inches. That's why we are dividing here the width in pixels by the DPI. And finally, this is going to be the total number of frames, which is going to be a multiplication of duration and frames per second. Then we're actually going to repeat some of the steps that we did for the static map. We're going to be using the matplotlib to create our map. The first thing is to define the size. So we're going to be using this fixed size that we previously defined, also the DPI that we previously defined. And then we are going to go and a bit customize our map. The first thing is to define here the left and right, so 0, 0, and then followed by 1 and 1 for width and height, and not 0 and 0, so 1 and 1 at the end. Then after that, what we're going to do is we're going to set the colors of the plot that is not going to be completely covered. So we're just going to turn it into black. So there's a nice transition between the base map and the margins. Then we're going to completely turn off the the ticks, the axis labels, and the title. And finally, we're going to also be defining here the bounds for our longitude bounds and our latitude bounds as well. So they simply here are going to follow the convention that we used for the previous static map. The next thing, we're going to be adding the base map. And again, for the base map, we're using Cartodb and the dark matter. So we are just, again, calling contextually providers function, and then we're going to, in the next step, then add this base map to our main plot. And this is something we did in the previous step. So again, we are making sure that the coordinate reference system defined here is the pseudo-Mercator EPSG3857. Just like we did for the static map, we're going to be also adding this smooth optional boundaries of grease in white, but not very pronounced because we don't want to suffocate the lights on the map. So we are here defining basically the same things. Line width, it's going to be 0.6, and then the alpha value, it's going to be also very low. Color is going to be white, and here for Z order, we're going to be defining as 3. All right, time to add also the lights to our map. So we're going to start off by actually, first of all, here extracting the X and Y values from our lights object, of course, the one that is using the Mercator coordinate system. So after we extract the X and Y values, we're going to go ahead and then, first of all, define the glow of this one. So this is going to be the one that is going to be expanding as we animate. And this one is going to have a bit bigger size, 60. And then also the line width here is not going to be present, but the alpha value is going to be a bit smaller. And then going to go ahead here and define the color. Now for the color, at first I was defining yellow, but I decided to go for a bit smoother yellow version here, so that I don't really, destroy your eyesight. So that's going to be the first one. And then the core one is going to be the base one, basically the one that you saw on the static map. And that one is going to be much smaller in size, so 9. It's going to be again point, but it's going to be in a bit different way organized. So its alpha value is going to be a bit more pronounced. It's going to be 1. And then for the color, it's going to be white. Also, it is going to be a bit bigger. Okay, then we are here going to define how, first of all, the scene is going to look like. So we're going to be creating this update function. Basically, it's defining by frame how the scene changes over time. The first thing we're going to do here is going to be converting frame index to elapse seconds, because this is going to be making timing independent of the actual render speed. Then for this pulse, we are going to be defining a smooth scalar, so it produces a very gentle breathing rather than a harsh off, blinking. That it, again, is going to affect your eyesight. And then we're going to be using in the next step this glow set alpha to actually animate the glow opacity between 0.05, 0.35 to keep the halo actually faint at the minimum and then pleasantly bright at the peak of the scene. And then the fourth one is going to be a setting for the core, so the base one alpha, and this one is going to be visibly pulsed. So this wide range is going to make it obvious by putting the opacity between 0.20 and 1. And then at the end of this one, we are just simply going to return these two values that we created. Then let's finally build the animation controller. Over here, we're going to put fig, which is figure to animate, update, which is the per frame function, which we previously defined. Frames are going to be defined here as total frames, so how many frames to produce. Interval, which is 1000 divided by a frame per second. Basically, it's milliseconds between the frame, approximately 55.5 milliseconds. Then after that, the split equals false means safer with the tile maps, and then repeat equals true means that it's going to be basically done. It's going to be basically loop after finishing this one. And then finally here, if you want to have this inline in Jupyter, you can then just run this also, this anim, and then inline you will see the animations. Once this object is rendered, we can go ahead and save this as a GIF file. First of all, we're going to be defining the name of the file, which I'm going to call here Greece underscore lighthouses, and then dot GIF, which is very important. Then we're going to be here also making a directory, unless it already exists, or otherwise we're just going to be using the parent directory where this is stored. And after that, we're just going to go and save our animation as a GIF file. So basically here, what we're defining is just, what is the output folder. And then for the writer method or writing method, we're using this pillow writer, defining here, of course, the frames per second, and also the DPI, which we already had as constants at the beginning. And then here the final line is basically simply, okay, save this as an output. All right, ladies and gentlemen, here is our lighthouse map of Greece, animated lighthouse map. And I really like how it blinks and also gives us a bit of a pause before unleashing its beauty. The good thing is you can make this for any country in the world. Just follow my tutorial and just replace Greece with your country of choice. Of course, you can also tweak these lights as well, the blinking, the frame rate per second, maybe the quality of the image as well. Anything you actually want, it's possible. But yeah, let me know in the comments what you think about today's tutorial, what you think about the map, and what is the map that you plan to make soon.